let's say, target to set the scene is to remind everyone and have the same page about maintenance. So for the railway domain, I mean. So maintenance here, I put some well-known definitions in our, let's say, railway domain. So maintenance can be described as a combination of all the technical and administrative actions. I mean, both are, let's say, to be considered, including some supervision actions. And the main goal is to retain an item in a healthy operational state. And to restore it when it's not in a healthy operational state to a performer of required functions, let's say, related to some objective. Second definition that is also well known in the literature is the goal of maintenance is seen as a total life cycle optimization of an asset. So let's talk of an asset. Here it's put an item, but now we are using the term assets everywhere. So let's keep it as an asset. And so the maintenance involves all the, let's say, data collection, and to make this data collection information, so you need some kind of transformation and processing, data processing, and that you need to set goal and translate these goals to this objective. So to achieve the objective that are considered by all the railway organization. And so to monitor this performance according to this objective, you need to define some key performance indicators or KPIs. So I will go maybe through this in some later slides. So the main purpose of the maintenance is to reduce the business risk, and the business risk is seen as for the railway, what we call infrastructure managers, which is, let's say, the one who is responsible and owner of the infrastructure assets. The business risk may rise to some non-availability of the rail tracks, or let's say, or poor track performance due to some degradation first, and then second as the failure of the assets. And so when the business risk rises, for sure it will decrease your customer satisfaction if you are a railway operator, and some loss of revenue. So it's very important that maintenance is, let's say, considered as one major cause for the rail transport operation. Second, as to set the scene also, now that we have seen, let's say, all about maintenance, let's go through the maintenance policy, or sometimes called also maintenance strategies, which evolve over time in the railway sector to reduce the cost. As I said previously, this is one of the main purpose of the maintenance, but you need to maintain safety. So it's a kind of balance between cost and safety. So currently the existing maintenance policies are mostly, let's say, what is shown here as the first one is corrective maintenance, also known as breakdown maintenance. This means that the assets or components of the assets are replaced when a failure occurs and has been detected. So it's after the failure has occurred. So it's really, let's say, non-optimized maintenance. Second, existing maintenance policies that we can see. So most of the time it's a combine between corrective and proactive. And so proactive or preventive maintenance is that you replace the assets or components of the assets at regular intervals or fixed intervals. So now mostly in all the railway operators, it's a kind of combination between corrective and preventive maintenance, depending on the assets mostly. So this is based on, let's say, a principle that reliability and operating age of assets and components are linked. But this is not always the case, and this is not always true. And most failures give some warnings with potential, let's say, degradation to a failure before a complete failure. So that's why new maintenance policy are rising. I put 3 of them, but we will focus only on one. The first one is the condition-based maintenance, or CBM. I will let's say, provide some more explanation on this one. Then we have the predictive maintenance, which is the focus of this presentation. You have also a new, let's say, maintenance policy coming from other sectors like aircraft and so on, which is the reliability center maintenance that is considered as a combination of condition-based and predictive maintenance. But I will now go into details for this one. And so, as I said previously, there is a kind of right balance because of cost, because of complexity of solutions, and there is a right balance between preventive and corrective maintenance now in the railway operation and maintenance department. So this has to be understood. So let's go now jump to the predictive maintenance. So thanks to advanced statistical methods, which is, let's say, one of the focus of this symposium, such as machine learning. So it's now possible to set up predictive maintenance, which is considered as a dynamic definition and identification when an asset is in healthy operational state or need to be maintained. So maintained means you can identify the degradation or, let's say, the faulty states. So here I put a definition from Neurospace, which is considered as a prediction of future breakdowns, of future failure, by giving you a probability. So it's now a new, let's say, principle for the operation and maintenance department that is going to rise in the coming years. Condition-based is a bit different because it prevents additional breakdown caused by telling you that something is wrong now. So you have, let's say, it's mostly based on monitoring and diagnosis of the assets in real time. So it's a bit different. And predictive is, let's say, based on probability. One is important to know is that due to its, let's say, advanced statistical methods, predictive maintenance requires far more data than other maintenance approach. And this one is also a big challenge for railway operators, mostly for the one who have not, let's say, already began their digital transformation. And so it's very difficult to manage this very lots of data, how to put them as information, the quality, the format, the storage. So there are many challenges that rises. And the last point I would like to present to set the scene is now how artificial intelligence, what it could bring to the predictive maintenance policy. And so, as I said previously, one of the most promising area that needs to take advantage of AI is seen as predictive maintenance. That's what we have identified with all our railway members. So this is our, let's say, first focus to, let's say, assess the possibility of AI for predictive maintenance. So the maintenance cost of the whole railway system counts, as I said, for a major part of their recurring spending. And the introduction of AI will certainly drive a significant reduction of this cost. When I say certainly, so it's still to be proven. So it's also one goal of this, let's say, ongoing project is to prove that AI could bring and could drive some significant reduction of the cost in the maintenance area. AI for sure should bring and could bring some degradation models and predictive models in a machine learning environment, I would say, which can detect anomalies, which can classify the faults. So you need, let's say, a good challenges regarding failure modes, failure states, and then to predict the end of life, or it's also understood and known as the remaining useful life of the assets or component of the assets. So it's very important, let's say, first to set the scene before going down into the AI for PM. So now that the scene is set. So let's go to the essential parts. So first, some general information on the, let's say, AI for PM project. So it's, let's say, a 3 years project, 36 months, which started early in 2022 in Q1, around January, February this year. UIC is the lead coordinator, but we have, let's say, several members as a consortium, and the main topic is on digital technology. Here you can see, let's say, the members of this consortium. So it's made only with railways. So there is no industry, no vendors in this consortium. So it's only for our members. It's mostly from Europe. You can see ADIF, which is the Spain infrastructure manager, Irish Rail from Ireland, which is infrastructure, but we have also the rolling stock department, which is also an important part of the predictive maintenance. We have Deutsche Bahn from Germany as an infrastructure manager. We have FS, part of RFI, which is the Italian infrastructure manager. We have MAF from Hungary, which is also representing an infrastructure manager. EBB Infra from Austria, which represent the infrastructure domain. We have SBB from Switzerland, which represent both the infrastructure and the rolling stock departments. And last but not least, we have SNCF Réseau from France, which represent the infrastructure. So most of those 8, let's say, members of the consortium are already well advanced, mostly well advanced in their digital transformation. So they already, let's say, faces some challenges, mostly on data and technical challenges. So this is also important to note. Then the main objective of this AI PM projects. So the main objective is to assess the existing and the potential usage of AI applicable for the predictive maintenance in both domains, infrastructure and rolling stocks. So that's why we have, let's say, both infrastructure manager and railway undertakings as part of the consortium members. Our starting point was in 2 steps. The first step that has, let's say, finished yet is an inventory of all the use cases, the railway use cases on both domains where AI could improve predictive maintenance. And the second step is a generic assessment of the applicable AI methods and all the industrial tools, let's say, as a second step, as I said. So we started the assessment of use case first from the members of the consortium, and we extended our assessment from external sources like from other railway members, from other UIC projects. We have a dedicated working group related to asset management and all the, let's say, digital railways. And so with all the information, it's then possible to determine the areas of applicability, the feasibility, to identify the key elements of all the contexts, such as dependencies with the telecom infrastructure. It could be 5G, it could be IoT or whatever. The economic value of the lifecycle management, or also some generic analysis of impacts, which is mainly on safety, reliability, and punctuality, because as I say, we should find the right balance between the reduction of costs and the, let's say, the maintain of the safety of the whole railway activity. So also the second part of the objective, the project is considered by all our members as a way to develop a common understanding and let's say, and a global approach of AI usage in the railway sector. Predictive maintenance is one area, but it should, let's say, also drive the common understanding on other areas in the railway sectors. It's for decision-making people, not, let's say, mostly not only for technical guys, but also for decision-making peoples to facilitate the future investment and associated operation in the rail sector as a whole. So it's very, let's say, first step for the, let's say, research and development activity in the domain of AI in the railway sector. First, I would like to bring some framework. So the project is divided into work packages. So maybe you are familiar with this, let's say, split. We have 4 packages. The work package 1, WP1, is the assessment of the infrastructure domain. Work package 2, which is, let's say, conducted in parallel with the work package 1, is dedicated to the rolling stock assessment. So here we have all the railway undertakings as part of this, let's say, work packages. Then when WP1 and WP2 will be finalized, we will enter a third step, which is work package 3, which is a general inventory and the mapping with the AI method and the industrial tools. And then when it will be finalized, we will enter the last work packages, which is on impacts, as I said, on telecom infrastructure and the dependencies with some, let's say, other stuffs. But I will go, let's say, more deeper into this, let's say, work packages. First, a global view on the timeline. It's a 3 years project starting in early 2022, which will run under 2022, 2023, and 2024. Here we are in Q3, so we started in Q1, WP1 and WP2 in parallel. These 2 work packages should be ended in Q1 next year, 2023, and then we should start also WP3, but WP4 will not start before, let's say, Q4 2023 or Q1 2024. So each of these work packages will be finalized with one or various deliverables. End of Q1 2023, we will have at least 2 deliverables at the end of each work package period. And so maybe we would be able to share with, let's say, other members or maybe outside for other stakeholders the content of those deliverables, but it will be as a next step. Now I will focus, let's say, on the work packages descriptions. So I propose to start with the work package 1. So work package 1, which is related to infrastructure assessment. First focus on WP1 task. So the first task is to analyze and have a careful selection of the relevant challenges to be solved by predictive maintenance in infrastructure domain. So here we have already, say, quite finalized this task. We have identified, let's say, and split the challenges between multiple categories, like the business challenges, but also the, let's say, more technical and data challenges. As I said, and some of the members are already, let's say, entered the digital transformation. They already know what are the most data challenges to be tackled. And I think this one is also, let's say, linked with other sectors and railways. Data challenges are not only in the railway sector, but most of them are also similar in other sectors, in other transportation sectors. You can find the same kind of challenges. So it's easy also to have some inputs from other domains. The next task is about the partial inventory of inspection and assessment procedures, asset condition indexing and monitoring system. So here it's materials are coming from, let's say, the consortium members. And so the idea is to have some kind of generic procedures. Maybe we may have also a generic procedure for both infrastructure and rolling stock domains. I think it could be, let's say, the most promising one. Next is about benchmarking on some key parameters and existing models to predict degradation of infrastructure railway assets. So mostly it's based on the use case we have already identified. I will put some, let's say, slides for this use case later in this presentation. And so here we identify the failure states and failure modes per assets for the infrastructure. Next task is decision-making process. So remember that this project is also for decision maker to facilitate the investment for AI in predictive maintenance, but also for the other areas of the railway sector. So this one is to choose the proper monitoring to gather useful data. And the last task for WP1 is some recommendation on the monitoring system setup with some innovative solutions like IoT to be applied on the infrastructure railway assets. So for this one, we already draft some, let's say, functional architecture of the monitoring systems with some kind of functional blocks and interfaces between the blocks, but also external to the monitoring system from the data sources, but also to the, let's say, display system for the OEM guys, the maintainers, and also for the decision-making peoples. So one of the WP1 deliverable will be the partial inventories of the use cases on the infrastructure domain. And so I will show some slides later on. Next is about the rolling stock, WP2. So it's a kind of similar work packages, but dedicated to the rolling stock. So it's mostly input from our members also. So the first task is to collect data on some assessment procedures, on the avoidable degradation models, and or the existing onboard monitoring system. So it's also linked to the WP1 as we find some kind of generic architecture of the monitoring system. Next task is about the data analysis that can be obtained directly or via some measuring and monitoring system for the selected use case. Then we have to identify the possibilities and the limits of the existing system to prepare for future fields of R&D. So this is one important thing for you also. And then the last task is to define the thresholds, reference value, and all the degradation deviations to announce the possible failures of the assets in the selected use case. And so we are expecting some kind of deliverable with a partial inventory of use cases, but applicable for rolling stock. So when WP1 and WP2 will be finalized, so end of, let's say, 2022 or Q1 2023, we will enter the WP3, which is the general inventory and mapping. And so the description of the task for this work package are the, let's say, the consolidation of the inventory of the use case in both domains. And then, which is, let's say, maybe the most exciting part of this project is the generic assessment of the artificial intelligence methods, which may be applicable to the selected railway use case. So here we put some kind of example, neural networks, big data, machine learning, weak signals, and so on. Then we will have to identify the available AI tools and solutions, including their profile of usage, with the consideration of market players. So here we will have to make some liaison with some industry and AI vendors outside of our consortium members. And then the last task will be to map, to have a kind of mapping between the railway selected use case and the AI methods and tools. So this will finalize this WP3 task. So the main deliverables will be, let's say, 4 of them, which is the final inventory of use case first. Then we will provide some kind of guidelines for our members on all the AI applicable methods and tools for the predictive maintenance. Then we will have a kind of report for decision makers on smart selection of inputs for the AI for PM on the infrastructure domain, and the last report will be on the rolling stock domain. And then we will enter the final work package, would be the, let's say, the impacts on safety, reliability, punctuality. So to, let's say, keep maintaining safety when you introduce some new maintenance policy. So it's very important for the railway infrastructure. And also, in addition to impact, we will discuss about, let's say, dependencies with the telecom framework regarding the user requirements, IoT solution, telecom profiles, and so on. And then we will have some economic impacts of the some selection of the AI method and tools. And the deliverable will be a complete report for these different tasks I already enumerated here. Just looking at the time, okay, we should have some time to continue. So as a first step, we will, let's say we have already defined a kind of taxonomy of the railway assets, a classification in different assets groups from track structures, civil structures, signaling, telecom, blah, blah, blah. And so for all of these assets group, then you have a kind of subdivisions. Here we put an example for the track structure with regarding the point and switches, the tracks, catenaries, and so on. And for each and every assets of these groups and taxonomy, then we will have to define the characteristics, including the functional requirements, system requirements, including performance requirements, some kind of localization of the assets also for sure. This one is mostly important for infrastructure. For onboard, it's, let's say, more or less to identify where and which locals and trains the assets are embedded. Then on the assets characteristic, you will have to define the failure states, which is about effects, and the failure modes, which is about causes and consequences. Then I put also some use cases here where AI could bring some benefits. So we have already started to the assessment. So here is just for your information on the infrastructure domain first. So the first one is about track geometry, where you can find approximately 30 parameters that can be monitored and diagnosed on track geometry. And the sources, sources is more or less some measurement tools, or where you can find some information, is on the age and type of assets, measurement trains, trolleys and tampers, georadar system, clearance scanner, blah, 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 and so on. And so based on this data collection and data processing, the output prediction should be some tamping action and track renewal. Next use case is about rail wear and defects. And so you have, let's say, same kind of information. So data should be rail wear and surface defect parameters. And the sources and measurement tools should be profilers, grinder and video system like CCTV, fixed CCTV, the profiles, age, grade, profile, track alignment.
Excuse me, Mr. Bianca.
Yes, sorry.
And now it's like we have a limited time for presentation. You can like conclude
Okay.
your presentation for us, please.
Yeah, so if you want to know more, I will share, let's say, all this presentation that you will have some detailed assessment of the use case, some information of additional use case. And if you want to know more, I put also some link for further information and readings on UIC AI, where we are. And so you can, let's say, follow the discussion. And I put also my direct email. So if you want to know more, please send me an email and I would be happy to share some information. So thank you. That concludes my presentation, and any question from the audience are welcome. Thank you.
Okay, thank you for your sharing the knowledge, Mr. Kiyoas. And now we have one question from the audience, from the Dr. Suthi. And the question is, do you intend to apply the AI predictive maintenance standard to the new trend, or the exciting trend one is has been defined?
So first objective is a global study. The applicability will be as a second step. So maybe we will start a kind of pilot or experiment as a second step. But the first step is really to provide to all railway top managers and decision-making peoples the understanding of what AI could bring. So this is the first step first. Yeah.
Okay, thank you for your presentation from Mr. Kiyoas. And for the next topic is view and real maintenance planning with support of computer simulation. The speaker is Dr. Professor Sebastian Steichel. The Professor Sebastian Steichel, he get a PhD in the vertical dynamic from the TU Berlin, and now he have an 10-year experience work from the Bombardier Transportation, and after that he joining to the KTS Royal Institute of Technology in Sweden. And now Dr. Sebastian, Professor Sebastian.
Yes, I am
Yeah.
here. Thank you
Okay.
very much for your introduction and good afternoon, everyone. Can you see my screen already?
Yeah, we can see your presentation.
Yeah, full screen also.
Yes.
Yeah, very good. So thank you very much again for the introduction and good afternoon, everyone. As said, I'm professor at the Royal Institute of Technology in Stockholm, Sweden, and I will present on wheel and rail maintenance planning with support of computer simulations. Besides me, a lot of colleagues have contributed to what I will present here today, and I will take up several of the issues or points that have been mentioned by my colleagues earlier in this session. So I think that fits together quite well here. What am I going to talk about today? After a short introduction background, I will firstly have the calculation of rail damage and possibilities to optimize grinding intervals as one use case, and the second one is wheel life prediction and planning of wheel reprofiling intervals. As a background, why do we deal with this topic? According to information we have got from the Swedish infrastructure manager Trafikverket, about 40% of track maintenance renewal costs in Sweden are attributed to rail wear and rolling contact fatigue. That means rail surface damage. Another issue is also that these both phenomena are interlinked. If you, for example, have wear, then initiated cracks could be worn away. So you cannot just look at them isolated. You have to deal with them in combination. And another thing is that maintenance activities as were also, for example, influence the wheel rail dynamic interaction or the vehicle track dynamic interaction. So it is a very complicated process that needs a very thorough investigation to make good predictions here. So our aim is a little bit, as what has been said earlier by colleagues, to provide a tool, a framework for prediction of wheel or rail damage. And the overall goals are to achieve a higher infrastructure availability, reduce maintenance, the amount and the cost of maintenance, reduce costs due to delays, lower operating costs. Yeah, several things. To be able to do this, you need a prediction model, and such a framework we have worked on for many years now at our university. There are a lot of parts that are needed for such a prediction tool. You need advanced, quite accurate multi-body simulation models. You need to deal very detailed with contact mechanics. You need to have the damage models. You need to deal with numerics because you need a lot of iterative calculations that take a long time, and so on and so on. You need to validate your simulation models, and that means that to come up with such a framework is not done in a short time. And as you can see with this timeline here, I just want to indicate that we have been dealing with this for more than 20 years. Now the first thesis we had in our research group on that was in 1999, and since then we have continued to work to refine our calculation framework. We have had PhD thesis only on contact mechanics to improve the prediction of the size and shape of the contact patch, for example, and the stresses arising in the contact patch. And all these works resulted in what I'm presenting today. And the first example is the calculation of rail damage, and as said, how you can use it to optimize rail grinding intervals. For the model, firstly, you need the vehicle model. You need as much information about the track you're running on, and you need information about the operation. And what does that mean in more detail? Yeah, for the vehicle model, you need the parameters like masses, inertias, spring and damper characteristics. You need to know whether there's flange lubrication or not. You need to know something about the traction system. And when it comes to the infrastructure, you need to know track layout, track geometry, track irregularities, the rail profiles for the vehicle. Of course, you also need the wheel profiles. And then you need to know something about the operation. What are the speeds? How much traction and braking and other inputs? What is the friction, for example, on the line? So there's a lot of information you need. And then you can build up your simulation tool to assess long-term accumulated rail surface. And firstly, we do this due to the vehicle passing. We choose a rail cross-section, and then we need to know what type of vehicles are running on that cross-section, how often, what is the proportion of different types of vehicles, locomotives, wagons, and so on. With that, we build up the load collective, the operational case, and then we calculate the forces, creepages, stresses in the contact, and that we use as a processor to calculate both the wear on the rail and the initiated cracks. And after a certain time, we update the wheel profiles and do all the calculations again until a certain tonnage that has passed that rail cross-section is achieved. And then we output the key damage indicators. You will see a little bit later how a result can look like. Recently, one of our PhD students has worked on adding also the grinding action to that. With in certain intervals, the rails are grinded, and that of course changes geometry of the rail, and that changes the vehicle track interaction. So as you will see in the results I will show very soon, that is also taken into account because it is an important part and contributes to the whole life behavior of the system. Also recently we have been working in a European research project within the big research program Shift to Rail, and one study we made is to compare two types of freight wagon running gear. On one hand, the standard Y25 running gear that has been used for many decades, and then a new running gear developed by Tatra Wagonka in the EU project. It is called the Freight Rail Boogie because the project was called Freight Rail, and that featured cross bracing between the axles to provide a better curve steering, double Lenoir links to make the suspension a bit softer, better radial steering in curves, and also increased side barrel longitudinal clearance. Yeah, I think I don't need to say this again. This is a little bit, again, you need to know the vehicle design, the track operation, and then the maintenance actions. How is the grinding carried out in detail? And then with that, you can start iterative simulations. As said, after a certain time, the wheel profiles are updated, and then also after each grinding action, the wheel profiles are updated. And what you will see here on the left side is how the rail wear develops for the two different boogie designs. Here you can see how the crack growth develops, and here you will see after each grinding we have assumed in this calculation that the cracks are totally removed. So after each grinding you start with 0 cracks, and here on the right hand side you will see how the cracks would grow if you would not remove them by grinding. So I will start this here, and you see how we iteratively calculate on the left side, as said, where, and the jumps are always the grinding action, and when it grows slowly, this is due to vehicles passing. And yeah, in the middle and on the right side you can see the crack growth that is calculated. And after 100 megagross tons, wait, sorry, now it's starting again. That was not. You can see that there's a difference between the two boogies. For the new freight rail boogie that has better curve steering properties in this 450 meter curve, for example, the brake initiation is much more spread out, and you will not have that severe cracks that you have with the standard boogie. So you can very easily assess how the boogie design influences the damage development on the rail. And here you can see, for example, what you can see on the vertical axis is how many contacts after a certain tonnage exceed the yield stress limit. I will come back to this a little bit later when I talk about the wheel. And you can see the standard UIC Y25 boogie has much more exceedances of the yield stress limit than the new softer radial steering freight rail bogie, and that would give you opportunities to modify your grinding intervals. Probably if a line is mainly operated by freight trains with these bogies, you don't need to grind the rails as often. But you can also use this tool to investigate how weather conditions or operational changes or wheel profile changes influence the behavior. If you know you have had a period with very dry weather, very high friction coefficients, you could redo the calculations and see how much earlier do I probably have to grind because of that, or if I do any operational changes or change the wheel profile, you can calculate again and estimate after how much time, how many mega gross tons do I need to grind the rails. Very similar, we work also on the calculation of wheel damage and the wheel life prediction. And the case study I will present here is on the Swedish iron ore line in the very north of Sweden. It's a very demanding type of traffic. The freight wagons have an axle load of 30 tons. It's, I think, up to 68 wagons with 30 tons axle load. As you can see there in the winter, it's extremely cold, down to minus 40 degrees. And there are also quite steep downgrades from the mines in Kiruna down to the harbor in Narvik, where the ore then is shipped to all over the world, and also quite narrow curve radii on that line. So very demanding traffic. And you can see the development of wear and the cracks on the wheels is closely monitored in the workshop. And here you see, I hope you can read it. You can see the probability that a wheel needs to be reprofiled as function of the mileage. And you can see after already 40,000 kilometers, about 50% of the wheels needed reprofiling. So it's quite often, and if you can predict that, or can with some measures perhaps even extend that interval, you could earn quite a lot of save quite a lot of money. The logic for the simulations is very similar. Again, you need your simulation framework with knowledge about the vehicle, the track, and the operation. This time the load cases look a little bit different. This time you don't look at one rail cross section, but you look at one wheel set and need to know on which curve radii and on which network does that wheel set or that vehicle operate to simulate an as realistic operation as possible. And similar again to what I showed earlier, we do the calculations, calculate the wear of the wheels, so the change of the wheel profile, calculate the crack initiation, and after some time we update the wheel profile. And when the desired running distance mileage is reached, then we finish the calculations. A little bit more about how the rolling contact fatigue calculations are done. Each time a certain cross section on the wheel is in contact with the rail, we calculate the stresses and we calculate if the yield limit in shear is exceeded. And if it is exceeded, we increase the count, 1, 2, 3, 4, how many times that is exceeded, because that is a good indicator of the risk for rolling contact fatigue. As I said in the very beginning, wear can help to reduce crack growth. So what we do is also we correct the crack growth with the amount of wear we have. If there's very little wear, then we do not correct the crack growth, and then with a linear function between two different wear characteristic wear values, the correction factor is changed, and if there's very much wear, then we even can say that there's no risk for crack growth because all initiated cracks are worn away. And with this framework, for example, you can do qualitative studies. We were asked by the iron ore company, what happens, for example, if I do not have electrodynamic braking on the locomotives that would reduce the creepages and the stresses that arise in the locomotive wheels. So we can look at this, what happens if I use a different wheel material. Another issue is they are interested in further increasing the axle load. What would happen if you increase the axle load, and how does the picture change with respect to track gauge, because there are quite a lot of problems with gauge widening on that line. So up to now it was possible, or up to then it was possible to do qualitative studies, but we wanted to do also quantitative studies. We really wanted to be able, after how many exceedances of the limit in shear stresses do we really have a failure, so to really assess the fatigue life. And here are some laboratory measurements that colleagues from Chalmers University have done, helped us to calibrate our model with the Wöhler curves they have measured in the laboratory. We could calibrate our model to really say after how many exceedances of the shear stress limit do we have a failure. And by that, then you are not only able to make qualitative but also quantitative assessment. And as you can see here on the next slide, we can now then calculate similar curves like the ones that are based on the workshop observations. We can say after how many kilometers of running distance do you probably have to reprofile your wheels, and that actually coincided very well. We detected with the with the field observations, the observations in the workshops. So we were really able to predict how many wheel sets of the fleet would need to be reprofiled after a certain distance. And that, of course, will help you with the maintenance planning if you can predict in advance when your wheel sets need to be taken in for maintenance. That is a big advantage for the workshop. Here just one example where you can see how the wear on the locomotive wheels develops. We have calculated up to about 100,000 kilometers of running distance, and you can see how it develops from new to worn wheel. And we have also compared our simulations to measurements and have seen that there's a very good coincidence here. For example, you can see the development of the flange height as function of running distance, and our simulations coincided very well with these field observations. And then finally, like for the rail damage, even here you can study a lot of influences. Again, how does the probability of reprofiling need change with wheel rail friction, for example, or if you take away lubrication, there is both flange lubrication but also track lubrication with friction modifiers, but that does not always work, partly because of the harsh winters. So you can try to predict how many more wheel sets do you need to reprofile if the lubrication does not work, as said, if you don't use electrodynamic braking, if you change the loads and so on. So you can really use this as some sort of digital twilling to predict how the system will behave and how your maintenance needs would look like. So just to conclude, our tools that we have worked on for a long time show very good agreement with field observations, and we believe that they can be used to optimize rail grinding or wheel turning intervals with respect to which track section, operational changes, vehicle type, change of wheel or rail profile types. And just one final comment. What we are also looking at in the next step is to extend our physical models. They are based on the physics right now, extend them with machine learning algorithms to further improve the prediction capability. And with that, thank you for listening, and I give the word back to the chairman. Thank you.
Okay, thank you very much, Professor Sebastian, for your sharing the knowledge with us. And we can see it's like Dr. Sebastian is uh, doing the research about the wheel right profile like in the 20 year. And now we have one question from the Dr. Siti. And have you already taken the remote mechanical effect in the model?
No, up to now, we don't take into account that the temperature changes when you are braking, for example. So we don't calculate hardening of the material, for example, because of high temperatures or so. Good question, but that is not included right now.
Another question from Mr. Turkiet. What are the main factors to specify the reprofile interval? And it means like how many times we should do the reprofiling.
So the main influences are, on one hand, is definitely the vehicle design, the type of running gear you have, especially when you have relatively curvy lines, but also the wheel rail profile combination is extremely important, because that determines where you have the contact patch, how big the contact patch is, and which stresses in the contact you get. So these are very important factors. And how often you should reprofile depends really very much on the type of traffic on the iron ore line where I presented. As said, often you have to reprofile already after 40, 50,000 kilometers. But if you have a high-speed line, wheels of a high-speed vehicle can sometimes run 400,000 kilometers, or say between 200,000 and 400,000 kilometers before reprofiling. So that really depends very much on the type of traffic.
Okay, thank you very much for your answer. And if another audience have a question, we can pass the question to you after this
Yes.
by email.
Mm-hmm.
And
Yes, of course.
yes, thank you very much. And now the next section is a panel section that is moderated by Dr. Chaluwat and Dr. Suthi from the Real and Modern Transport Research Center. I will pass this section today, please.
Okay. Now we have time. We're gonna start the panel session in the topic of the digital twin for the future mobility. So today we have three panelists from the private company. The first one is the Mr. Srilankarajan. He is a managing director in Altai Engineering. So I will give you a short bio of Mr. Srilankam. Mr. Srilankarajan is currently the managing director for the Asian and Australian New Zealand region for of Altai Engineering. So which provides I think Altai Engineering is is a well-known software and cloud solution in the area of the simulation, high-performance computing, and artificial intelligence. And the headquarters is in Massachusetts, USA. He established, Mr. Sri Lanka established the regional headquarters for the Asian region in Kuala Lumpur, Malaysia. Can you say hi, Mr. Lanka? Hello, Mr. Hello, Lanka. Let me check the panelists. Okay, hi. Good afternoon. Can you turn on your microphone? I think we cannot hear you. ได้ยินไหมได้ยินไหมได้ยินเลย Okay. By the way, we will introduce the next speaker in the panelist is the next one is Mr. Justin Woi. He is a sales distributor channel in the space GmbH. So Mr. Justus Woi earned a master degree in automotive engineering and transportation from Aachen University. His background involved creating a hardware in the room bench for an electric vehicle. He is presently working for the Space GmbH as a sales distributor channels.
Yes, thank you
Hello.
too for the invitation. So, hello everyone. Can you hear me?
Okay. Hi, Mr. Justice.
Hi.
And the third one, Mr. Robert Roman. Mr. Robert Roman graduated with a master degree from Nijrode Business University in Netherlands, and he facilitates project engagement and market approach. He has worked in the automated transit sector, introducing self-driving car to port, park, and public transportation. And now he serves as the director of ADAS, AV Business Development at Siemens Digital Industry Software. All right. Hello. Robert. Okay.
Nice to see you.
It's nice to meeting you all. So
I think what we're going to be doing today is that we're going to let every one of you give a short presentation on the topic. So I think we are going to start with Mr. Sri Langam. So you can go first if you are ready, and then we can. After that, we can then move to Mr. Boyd and then Mr. Lohman. Is that okay with everyone?
Yeah. Are you able to hear me now?
Yep.
Yeah.
Right.
Oh, fantastic.
Okay.
Are you able to see my screen?
Right. Okay.
Yeah. Okay.
It's pretty full screen now.
Sorry.
Yeah, please go ahead.
Okay.
Go ahead.
Thank you so much. Sorry about the audio in the beginning. Hello, everyone. Good morning, good afternoon, good evening, wherever you are. Since for the last 2 days, you would have had enough to listen, I thought I'll just give a very, very short presentation, probably for 2 minutes, and a couple of minutes, not just 2 minutes. And then probably take questions from you. To start with, who's Altair? We are. Oh. Moving. Yeah. We are a 37-year-old company with over $500 million in revenue, and we have over 3,000 engineers and scientists working for Altair, with over 15,000 customers globally and 86 offices. We have multiple partners, and we provide the partner software free of charge to our customers. I'm going to just focus very much on the railways and mobility and stuff like that. So we have a huge number of customers that we work with in different segments of mobility. This is the railway market alone. And if you look at the automotive, every other automotive manufacturer uses our software for either engineering or for data analytics. Now, very quickly, I wanted to leave a thought. What is a holistic digital twin? Since the topic is about digital twin, how do we perceive, what do we think is the digital twin, and why do we feel whatever we have to offer is holistic in nature? Let me just start with this video, and then you're able to hear.
Twice as nice. Are you digital twinning? As product complexity continues to increase, becoming more intelligent and more connected, planning for current and future products is no longer a nice to have. It's a must. Altair's holistic and flexible digital twin platform enables companies in all industries to improve product performance and maximize product life with simulation-driven design and CAE, communicate and manage large amounts of data efficiently through scalable IoT solutions, and derive maximum insight and value of operational data available with data analytics. How? With two types of digital twins, data-driven and physics-driven. Data-driven digital twins help extend the life of current generation products by obtaining and leveraging data about their operations. Data generated by numerous sensors and embedded systems, for instance, needs to be visualized fast to make informed decisions about how to adjust the operation of the physical asset, such as when and where to perform predictive maintenance. Physics-driven digital twins help companies develop future generation products by leveraging 3D and 1D modeling and simulation in order to develop better new products faster, optimizing product performance and saving development time and money. Combining IoT, machine learning, and data analytics with full digital simulation from 0D to 3D, Altair's digital twin platform creates added value in multiple ways, optimizing products' performance, reliability, and extending its life cycle, as well as helping make smarter, faster, and more informed decisions to improve on next-generation technologies.
Okay, that was just to give you a quick overview. Typically, what we see is people talk about the operational twin. So what they do is they collect the data from the field and they try and update the model, and they call it as the digital twin. So for us, that's only one part of the story. That's the operational digital twin, and that is very much data driven. If you look at, a holistic one is supposed to have a lot more information embedded into it, and it's supposed to connect to various silos of information, various departments where it collects information from. Like it will have information about the concept design, the detailed design, the simulations, both low fidelity, high fidelity simulations, reduced order modeling. It'll have data about other systems like MES, ERP, manufacturing, and obviously coming to the operations, the operational data collected through the sensors and various other means. So the constituents of the holistic digital twin will be physics-based, data-based, manufacturing, production, as well as operational, and it would sort of contain data which is enterprise-wide, as well as very specific to a particular product that is operating. So that's what we call as the holistic digital twin. So I leave this thought here. I can have a lot of discussion around it, but I just want to keep it just crisp and sharp. And if you have any questions, I'll be more than happy to take them. Is it okay?
Yeah. Thanks a lot. So we can now move on to Mr. Boyd. So if you are ready, please go ahead. You can share your screen.
I'm ready. Can you already see my screen? Should be visible. Would you briefly confirm?
Right.
Yep.
Perfect. Then I'm going to start. Yeah, thanks for the invitation. Good afternoon, everyone. So my name is Justus Vogt. I'm account manager at DSpace GmbH, the headquarter here in Germany. And in DSpace, I'm responsible for the Southeast Asian market. And yeah, as you already said in the introduction, my educational background is automotive engineering. I'm very happy to see there are also panelists from my alma mater, the RWTH Aachen University. But in opposite to many panelists today, after my graduation some years ago, I have not become a PhD student, but started a job in automotive industry. So my goal today is to give also some insights and trends we see when talking to industrial customers. Today, my focus related to megatrends in future mobility is, yeah, as you already said, the digital twin. Due to the limited time, I would skip the DSpace introduction now. Probably many of you, at least in the automotive area, know us as a partner in simulation and validation related to electronic control units. And if you have further questions, please do not hesitate to contact me. I think 10 minutes was the time for the presentation. Is this correct? And then I would just start, and I mean, you can maybe interrupt me at about half the time. So I would like to start with the motivation. So what is a digital twin and why do we actually need it? Simplified, a digital twin is a copy of a real vehicle and its environment in simulation. So when testing and validating electronic control units, we are not talking about quality assurance anymore, or not only. Quality assurance and the goal to find failures very early through hardware in the loop simulation, for example, has been the goal of our customers for the last 30 years. These customers are, for example, automotive OEMs and tier ones. But nowadays it's getting more complex. We are talking about ADAS AD algorithms. Those ECU architecture and algorithms are not only more sophisticated, but in the worst case, they can decide about life and death. Therefore, there are lots of regulations, as you can see here, for the homologation process before those algorithms and vehicles are driving on the street. And this slide gives an overview of certification. Of course, real-world test drives play a crucial role, but as time to market is one major point for every automotive manufacturer, they want to run more test kilometers faster with automation and reproducible. And these are the benefits physical calibration tests and simulation is giving. So we saw the presentation of Altair, who are more focusing on the mechanical parts, and we are also more focusing on the simulation part of the entire vehicle and traffic participants. So this slide shows, for example, testing of an ALKS, so an automated lane keeping system. And a vehicle equipped with an ALKS has to be tested with thousands of concrete scenarios. And when we are talking about this, then we are talking about scenario-based testing. As you can see in this picture and in this sheet, the scenario is already exactly defined in the regulation. And this is one test case for the ECU under test in a simulation environment with a digital twin of the vehicle and its environment, for example. But let's go more into detail, how to create the digital twin. At first, we can use real-world data. Over here, we can see a driving maneuver of a car, which was controlled by human beings, so nothing special. The scene was recorded in Korea from the perspective of a camera, which was mounted in the car. And this is the typical scene, no corner case, just a car navigating through the streets. But now imagine you have to test and validate a complex autonomous driving system, which is responsible to take control of the car and bring the passenger safely to their destination. So how you can test such a system? One way is, as we see, the real test drive. Here we take our vehicle with the ECUs and check how it behaves. If the system has not validated beforehand, this is of course extremely dangerous. Typically, such drives tend to be carried out in a closed-off test site, like a proving ground. And the advantages of this type of test is, of course, it's maximally realistic. The sensors interact with the environment, and the control units communicate in real time. Of course, this approach also has some disadvantages. So on the one hand, it remains dangerous because if you want to recreate driving maneuvers and don't yet know how my vehicle will react, dangerous maneuvers may well be the results. The next point is reproducibility. Reproducing a test twice in the same way is extremely difficult. So what if we record the sensor data from our real test drive? So I'm talking about camera data, radar data, LiDAR data, and ResBus data. And we simply store it on a data storage at runtime. And when we are back in the lab, we can play back this data in real time and either feed it to our algorithm as part of software in the loop validation, or even the complete ECU, including the timing behavior in hardware in the loop environment. The sensor data was recorded and therefore is maximally realistic. Since the test driver typically moves the vehicle during the recording, this type of test is relatively safe. And the next point is reproducibility. What was a negative point with the test drive is here an advantage, since I can repeat the replay over and over again. What other disadvantages are there? The recorded driving maneuvers are fixed. I can't change them in data replay. To get further tests, these must be first produced at a great expense. Furthermore, the sensor setup can no longer be modified. This leads to problems, especially if the installed sensor technology is not yet finalized. And another weak point is that these are exclusively open loop tests. So if, for example, my algorithms decide to break, the data replay will not take it into account. So how can we now perform a test that does not have these disadvantages? One answer to this is a digital twin. For this, I start again with a test drive where typically a camera recorded data as well as LiDAR data is stored, but I do not use this data in the following to perform data replay tests. Instead, I use the sensor data to create a representation of the environment and extract the driving maneuver. The subsequent tests are simulations. So I have a model of the vehicle, the fellow vehicles, pedestrians, the sensors, and the environment. Of course, afterwards, I have all degrees of freedom to modify any behavior since this is now a simulation. And with good models, the data quality is still close to reality. Tests can be performed both as closed loop and open loop tests, and even critical driving maneuvers are still completely safe. The simulation is deterministic, and of course, we can vary every parameter. But how can such a digital twin be generated? With a scenario generation service from DSpace and Understand AI, we use recordings of cameras and lidars to recreate the environment, as well as a driving maneuver that includes the vehicle, the ego vehicle, but also the other traffic participants. So as a first step, you need to record the sensor data from your target environment. Next, we create a precise 3D model of the environment. For this, we rely on an AI-assisted automated way to generate labels for the environment and moving objects. And such a label is meta information about the category of the object, like a car, a house, with further information about its size. The environment is reconstructed as close as possible by generating the 3D meshes, as well as the materials for camera, radar, and LiDAR. And these materials are necessary to get correct results when a sensor interacts with the environment. This slide, you can see, for example, how the materials are interacting with the camera sensors. While the generation part also holds for dynamic objects, we make sure to reproduce the position of them with a high precision so that the objects are correct positioned at any given time. So at the bottom right, you can see the original recording. I can repeat this. And the other video shows the same maneuver simulated in Aurelion. As a small variation, you can see here, for example, that the color of the car in front of us, we change it from white to black. So let me summarize. As we saw, there are 3 different ways to test your hardware and software for autonomous vehicles. The first one was a real test drive. After building up the test car, we simply drive on the road and check if the system works correctly. The next one was data replay. You can go out on a real test drive, but you record the sensor data on a data storage. Then the recorded data can be replayed and injected into your target hardware and software. The last presented solution was simulation with a digital twin. Again, we here have to record sensor data, but instead of using it for tests, we are creating a digital twin of the environment and maneuver. And in simulation, we can use this environment and run any test, any kind of variations we would like to do, no matter if you want to test the driving maneuver or the sensor setups, we can do it. And as a last slide, I would like to show the following, the driving maneuver with different variation in terms of weather and time. The first scene, we change the position of the sun to shine from the front of the car. Having the sun in front of you results, for example, in lens flares, which clearly results in a negative impact on the camera's performance. How does your perception work in the same scene, but at dawn? Headlights are on, but the scene, of course, is way darker with just a little sunlight. And fog significantly reduces visibility. A lot of objects will be detected later than without having fog. So will your algorithm still navigate safely? And how do you perform in rain or snow? All right, so maybe you can give me a overview of the time. I would have 2 further slides how the entire simulation system works, but I can also leave it out and we go directly to the panel discussion. What do you prefer?
Thank you for your information, Justus. I think we can leave the other material for later discussion. And I think, yeah, for now, we can move on to Mr. Lohman. Mr. Lohman, if you are ready.
I think I am, or it should be.
Please go ahead.
Share my presentation. I hope you can see my screen.
Yes.
Yes.
There we go. So I took a little bit of inspiration from the title for today, and wanted to sketch you how future mobility actually impacts the work in the development that we do here at Siemens. And you are in well, considerations you're taking. Obviously, low costs, but it's be easy of use. Unfortunately, for most people, also the image of the type of transportation they use plays into this. So when you look into this, what you see in many discussions is that, and I found this picture on LinkedIn, which is a great source for discussion over the past weekend. Life with cars is, life with electric cars looks like, it's not much different than ultimately what life with autonomous cars looks like. Really looking forward to this is what modern cities are going through. Different type of vehicles. So whenever we are talking about trucks, automated buses, we're talking also about manually driven variants. A lot of pedestrian, huge complexity of and this is seen by everybody because I took this picture or this next picture from a sustainability report. But if you see the ranging from bikes to buses to shared cars, normal Mercedes to a mode of transportation that is best for their such direction about cars. Somehow it's about autonomous. It's automatically associated with cars, even though that's most likely not the scenario that it's going to be in the future. So when you are looking at a little bit of a higher level approach than but when you look at the trends that are
sorry to
something go wrong?
Sorry to interrupt you, Mr. Roman. I think that your sound is kind of wavy sound. It's loud and volume up and volume down. I'm not sure you are using the noise canceling.
No, I'm not, but I might not have been talking to the screen directly. Is this better?
Yeah. Now it's better. Now it's better.
Okay. Well, let me make sure that I don't turn away from the screen. Let me know again if it's bad, because then I'll need to hook up a microphone quickly.
Okay. I think this distance is appropriate now.
Okay, good. Thank you for the warning. So one of the trends that we see in the market is that we are moving from big data to good data. So to prove the safety of autonomous vehicles, is it not okay? One second. Sorry about this.
So one of the trends is from big data to good data. So if we're driving a lot of miles to prove the safety of these autonomous cars, whether you drive them virtually or whether you ultimately test them on the road, you want them to run the certain miles to make sure that the performance of the vehicle is as intended. There have been huge calculations about the number of miles that's required to prove that a functionality works. And that's the number of miles you need to drive without failure. So the 11 billion miles is a calculation that is valid for autonomous vehicles. If you're talking about um, um, uh, something more regular, like an ADAS, like an automated lane keeping system, the example that was just used, you're still talking about, after simulation, driving 1 million miles in public to make sure that the functionality is actually correct. That means that there's a lot of data being collected. So autonomous vehicles that will operate can collect up to 1 petabyte of data per week. And what you actually see is, when you have all the data, and they now refer to it as data lakes, is that if you want to find the right data that you actually want to use towards the future, you spend 80% of your time looking for the appropriate scenarios and 20% of your time actually using those data in the actual test that you're conducting. So there's a huge efficiency benefit there that we're looking to achieve. The challenge, obviously, is the explosion of complexity. And here you see a typical example of the sensory systems that are present on a autonomous vehicle. Again, a car visualized in this image could just as well be a shuttle or a bus. But what you see is that there's an immense amount of data coming that needs to be time synchronized and accurately captured. And then there's a huge amount of storage costs associated for data that might, not be relevant, because it might be just another copy of data that you have collected previously. So there's something to certainly tackle there. Similarly, when you're moving to public road testing, and this is a famous picture of the accident that happened in Arizona with the Uber car, where they state that 90% of all the accidents are caused by human error. That equals 1.3 million deaths worldwide per year. And I think that 90% is, let's say, should be taken with a grain of salt, because even if the road design is poor and a person is driving a car, and because of the poor road design is unable to prevent an accident, the cause of the accident is attributed to the person and not to the road design. So in that sense, that should be taken into account when looking at the 90%. If we want to make autonomous vehicles safer, and we are going for public road testing, it should be noted that when technology makes a mistake and causes an accident, that's seen as just as bad as 4 road accidents that are resulting from human error. So we as people are a little bit more forgiving about other people making mistakes on the road with lethal consequences than when technology does that. So when it comes to the safety level, this is also something to be taken into account. When we say, autonomous cars or autonomous vehicles should just be as safe as regular drivers, we might actually be setting the bar too low when it comes to achieving social acceptance. And I think that's greatly illustrated by this graph. And I'm not sure if you have the same morbid fascination as I have, but this is about micromorts, and that means the chance that you actually add to your own demise ultimately by doing certain activities. So you see that getting a heart disease is 1 in 6, but if you gradually go down, you see that motor vehicle crash is actually already a chance of 1 in 102, which means it's a very high chance that, you are actually ultimately passing away from a motor vehicle crash. And then when you go all the way down, all the way to the end, to the tip of this visualization, you see a train accident and an airplane accident. And the train accident is 1 in well, almost 180,000, and an airplane accident is 1 in 200, more than 200,000. So ultimately, what we need to do as a society is when we are looking at what safety is good enough, perhaps being as safe as a regular driver for an autonomous vehicle is not good enough, especially because autonomous buses, or let's say buses in general, are much safer than cars. I think from the top of my head, buses are factor 10 safer than cars are. So if we create an autonomous car that is just as safe as a regular car, it's still 10 times less safe than a bus would be. Another trend, and Mr. Voigt already touched on this as well, is that we see a trend towards standardization. And you have the different entities that are monitoring this. The ISO 262 is obviously very famous, but there's also the SOTIF standard and the other standards that the industry is gearing towards. And ultimately, if you look at the International Society of Automation, and obviously they're going to be a little bit biased, but 96% of the respondents to a recent survey said that standards will be important or even extremely important. So when you take that into account, what is the challenge there is that, well, anytime standardization is mentioned in an innovative industry, is that people are wary that their innovations might be constrained by standardization and regulations. But in all honesty, no government has ever put regulations in place unless they were pushed to put that in place by new innovations being brought to the market. And regulations require standardization because you need to be able to sign off on something based on standard best practices. So you get a very interesting interaction between innovations, regulations, and standardization, in which all the companies in the market are involved because we're all pushing in a certain direction. And when you see a common denominator existing, that automatically trends the direction of that being regulations and becoming standardization. Something that has a long history in the rail. It has a long history in air traffic, and something that is now becoming a requirement for car traffic and well, let's say road traffic, because I'm saying cars myself, road traffic as well. And definitely we should learn there from the rail industry and the airline industry in that respect. So as Siemens, what we're trying to do is we're trying to engineer innovation, and we see 4 pillars that are basically contributing to that. So modeling the complexity is something that we're trying to do in our digital twins, while at the same time enabling the insights by exploring the possibilities that give. So the various variations of scenarios are absolutely a requirement to be able to visualize in your simulation practices. Ultimately, and the 2 last ones are actually kind of nice because I think they're related to each other. You want to go faster, so you want to get to market as soon as possible with the right safety, while also staying integrated. If you disintegrate and you are only focusing on going faster, then the chances are you bring a product to market that will ultimately fail. And I think right now where the industry is at, the failure of one company actually means the failure of all companies because it sets back the industry as a whole. So what do we do as Siemens? And this is the most technical picture I'm going to give you today. It shows the workflow that we're working on. I'm not going to get into product names because I think that's not relevant in a presentation like this. And what you see here is what we advocate towards our customers, that our capabilities are in supporting them in achieving their goals. So it goes from recording of what a vehicle is actually doing on the road. So on the left-hand side is our capabilities of providing hardware and software to actually monitor what a vehicle has experienced on the road, create the scenarios based on that, and use a real-to-sim converter to actually bring it into a simulation model. The simulation model is something that you see in the middle. And that simulation model ultimately allows us to do unknown scenario identification. So we have developed a mathematical approach in which we can use the data that we recorded live to actually find the corner cases. So discovering unknown, unsafe scenarios that are difficult to find because you can't guarantee that you run into them while driving on the road actually is possible using this mathematical approach, and ultimately gives you the capabilities of also testing in simulation your algorithms against the scenarios that you didn't encounter while driving. All of the information that comes from these various parts of the chain is stored in two central databases. So when you look at the way that is in steps, and this is an example of the data recording solution, you see how we move from capturing it all the way through usage, through the various stages with the various capabilities that there are. I won't go into much detail here, given that we'll leave more time for the discussion. Sorry, these are all the let's say added values that Siemens sees that we can provide to our customers in the various stages of the data recording solution and analysis. Then when you look towards the digital twin and the AV simulator, you see that we clearly mapped the capabilities of the AV simulator and the value that we try to provide to our customers relative to the 4 pillars that we see contributing to these to the simulation. And that concludes my presentation. I'm looking forward to the panel discussion. Thank you very much.
Okay, thank you for the presentation. Yeah, it was very informative. I think what we are going to do next is that we're going to try to get the conversation going. So we over here at RMT, we kind of develop an autonomous driving system, as well as we also do vehicle design from ground up. So I think it's let's, for example, when we talk about a team that is similar to us, we develop an autonomous driving system. We focus more on getting a working prototype, getting our prototype into maybe a testing area, CAV proving ground, something like that. And I think this concept of using this digital twin is kind of relatively new. So maybe some of the people are still unaware of the capability of the digital twin technology. And so to make it short, it's just that I think the reason we are doing this discussion is that we kind of we are interested in kind of exploring this digital twin solution. So I think we as a national research center, we also have our partner in the automotive industry. So maybe we can talk about the importance of the digital twin technology in this automotive industry. So let me do it this way. I'm going to ask the question. So my first question would be, what would be the extra reason that you can give us so that it could be a push for us to explore or invest in this digital twin technology? So yeah, I think we can start with you, Mr. Lohman.
Yeah, so I think what you're looking at is a combination of going from, I would say, simulation to a closed test course to ultimately public road testing. And that's the stepwise approach provides a best practice, if you will, of making sure that the public in general is not at risk. And the correlation between what you see in simulation and what you see on the actual road is very important. And what we've done as Siemens in the past is, for instance, at the American Center for Mobility, which is a huge testing proving ground in the US, is we've mapped their entire proving ground in our pre-scan solution, and as a result are able to simulate anything that has been done on the site in our program as well, providing the people that are testing at that test ground with a good example of what they do in simulation and what they do in practice. And then you can start creating the variations to what you've actually done at the proving ground. So I think it makes absolute sense for a government agency to look at the way they can use simulation to support proving ground tests before allowing anybody to use public road testing.
And we are mainly, or we are often talking about, functional safety, and also we are talking about, the regulations, but it's mainly also about time to market, which is one reason for having a digital twin. You have simply the opportunity to do tests earlier. So when driving on a proving ground or driving on a public road, you always need the entire car. And when talking about a digital twin or a simulation in general, you can use just one electronic control unit connected to a simulator and simulate the entire surroundings. And then you can start already your testing without the entire vehicle being available. And this saves time to market. And this is also one of the main reasons why automotive OEMs and tier ones want to test as early as possible. This is, I think, even more important than the flexibility that they see in simulation to have more degrees of freedom. But of course, all in all, everything is needed. So you can't do a homologation process just with simulation. You also need the real road test data, or the public road test, or the proving ground tests. But you also need simulation in the future. This is also written in the regulations, because otherwise you don't have the chance to do so many tests and such a variety of tests in a short time to market period.
Yeah. So just to add to that, I guess Justice and Robert have articulated it pretty well. It's so very important to have the simulation data. So you need to do simulation on every aspect of the vehicle. You need to go into the details of each and every attribute that are important for a particular vehicle. And we need to come up with procedures to do the simulation really thoroughly, so that, if you look at the trend today in the fossil fuel sector, people are moving towards zero prototyping. So there are companies that we work with, they are large companies from across the globe. They want to carry out simulation to that level of depth and fidelity that they can avoid physical prototyping. Okay? And we have shown it in a number of cases already, where they can just trust the simulation results and get approved. In fact, if you look at even the approved agencies, they only look at a couple of tests, physical tests. All the rest of the use cases, or the what do you call this? The probabilities can be just simulated. You provide just simulation data, and they would approve it. So simulation is very important, and it has come of age in terms of accuracy. And I guess that's a good start. Sorry, we can't hear you. We can't hear you.
You're probably on mute. Yes, you are on mute.
Yeah.
Yeah, thanks a lot. I think those are compelling reasons that we should explore the digital twin solution in regards to this automotive industry. So as you may have already known that in Thailand, we kind of depends a lot on the automotive industry. So currently we are doing the conventional auto industry, which means that we rely on assembling ICE cars and vehicles. So I think people say that it's currently in the transition to go into the next era of maybe EV and something related to EV. So I think when we say EV, I think a lot of us automatically also thinks about the autonomous driving system. So I think my question would be, it's clear that the transition to this new era of future mobility is inevitable. So do you guys think the digital twin plays a role in transitioning from the conventional auto industry into this future mobility era? Who wants to go first?
Yeah, so probably I'll go first. You're right. In fact, what we are seeing is we work with quite a number of mobility companies, be it two-wheelers, four-wheelers, again, railways, and so many of them. When it comes to the two-wheelers, I guess they are a little ahead now. They have captured all kinds of data. They know how to capture the data of the batteries, for example, the BMS systems. Plus, they also have captured or started capturing. In fact, now I should say that they have already achieved a level where they have all kinds of data available, as in not only the state of charge and health of the battery, but also on how many kilometers it has run, to what routes it has taken. So they capture. They started capturing every small little detail about everything, I should say, starting from the routes it has the vehicle has traversed, to how many people have been sitting on the vehicle and how much time it has been running, to and the battery health, also the component health and stuff like that. So that's a bit amazing for us, and I'm sure this trend is going to continue until you have a personalized data of each and every vehicle that is there on the road, and you can go on to do predictive analytics on individual vehicles, and you can probably even avoid any kind of failure or breakdown on the road. So that's probably the ultimate goal of the digital twin. And yeah, we see that happening in the automotive industry, though they are at a little lower pace as compared to the two-wheeler, because the number of components, the number of things to manage is much lesser, I believe, in the two-wheeler industry. But we are working with a large number of automotive companies, railways, for that matter, and there are some uniquenesses in each of these segments. But looks like that's where everyone is going to move towards.
Yeah, I also agree. I can also say a clear yes to the question that the digital twin will be important for the future mobility, because when taking a look at all the vehicles that are planned by the OEMs, we only see connected, autonomous e-mobility. So we are talking about a very high complexity when comparing it to vehicles that were produced 10 years ago. So there is so much more software code inside that needs to be tested. So on the one hand, we see a clear demand, and on the other hand, we also nowadays can do such testing, because as you see, to have such complex simulations also with real physics-based sensor data, we need a lot of power. So we need GPU power, we need CPU power, and nowadays we have the hardware of the computers to run such complex simulations. And we have even the possibility to scale it up in the cloud, because we always have to have one thing in mind. When testing with a digital twin of electronic control units, we have to make the simulation in real time. If we are slower than real time, then we have failures. And for software in the loop simulation, we have to be even faster than real time to reduce the time to test and to reduce the time to market. So as long as we see connected and autonomous vehicles and safety related functions also in terms of battery management systems, I guess we will definitely have more and more simulation, and we will have more and more digital twins in the future.
Yeah, from my perspective, I'm not going to disagree with the previous two speakers. I mean, we're all in agreement on this. The digital twin plays a role, but I would argue that it's a supporting role in what is happening in the industry. And I would say that the industry in general is driven by the directives that are setting by local and national governments. So in Europe, we see certain requirements with regards to ADAS systems now coming into the Euro NCAP testing. So if you don't have lane keeping assistance or other kinds of advanced features, you get scored less. So I think as a government, there's a role there to drive the transition towards ADAS systems and towards AVs ultimately by setting regulations and requirements for new cars that are being brought on the road, or for autonomous shuttles, or for anything else. Also looking at how quickly things are advancing, I think it's important to keep in mind there's a difference between ADAS and AV. And we sometimes happily confuse the two or throw them onto one pile. But I think for, well, if you're looking towards the cities of the future and the different kinds of mobilities that you'll see in those cities, there's a huge task and a huge challenge towards governments to find out which modes of transit go where. And then when the modes get settled, then the appropriate digital twins will come into play.
So we are kind of a government agency, so our role is to support the industry. So I think one part of the role that we play is to develop kind of a human resources. So I think with, let's say, a newly grads fresh from college students, I think there are taught certain ways in terms of working on design process and everything. So do you think there's an advantage to maybe kind of do some kind of a paradigm shift for this new wave of human resources in terms of maybe introduce them with the advantage of switching the thought process into relying on this digital twin technologies as opposed to maybe conventional design process. Any thoughts on this topic?
I think it's clear that you need both. So there is still the conventional design process, and so I think the first good point is that there are so many engineers because they are so heavily needed on the market. And yeah, as being an engineer myself, I can only recommend this job, and I think all of us. But to answer your question, I think both is needed.
I guess it is important to, in fact, we are working with a few universities in modernizing their curriculum to suit the industry needs. And one of them is we are introducing courses on digital twin, more so in the mobility space. So yeah, I mean, it is very important to sort of change or modernize the curriculum to suit the industry needs and be a little bit futuristic or have the education a little bit future proof. We are working towards that as well.
Yeah, I mean, you've got to appreciate the new insights that you always get from people that are just entering the industry, come out of their, well, are part of a new generation. and to typically have a different approach than the older generations. And you want them to both learn from each other. So the way it has been done is a good example of what has been proven, but the new generations often come in and grow up with new technologies that also create new possibilities. So it's a combination of both, right? You can't rely on what you have done in the past, and you can't fully rely on what has not been proven yet. So ultimately, the combination of both is absolutely required.
Okay.
So I think when we talk about autonomous driving system, people always think about maybe ADAS system. So I think for its importance for everyone in this field to kind of work on development of this ADAS, maybe algorithm development as well as testing. So digital twins, again, does it play any role in helping development of ADAS development, algorithm development, as opposed to maybe conventional approach? Or maybe I'm not making myself clear. So
Those questions, at least I did not get it completely.
Same here.
Yeah, so I think, well, we kind of are running out of time, so I'm kind of in a bit of a hurry. So, as a person doing ADAS algorithm development myself, my approach now is kind of work on maybe a C++ code, and we do some kind of iteration with the maybe using GPU computation. So do you think maybe digital twins technology can maybe complement this kind of work, this line of work that we are working on right now?
So you mean whether you can integrate your own C++ or C source code to interact with sensors, with actuators, and to run your algorithms in an environment?
Something like that.
Yeah. So basically, I don't want to make advertisement here, but for universities, we have, for example, free licenses for RT maps, and this is exactly a kind of a middleware where you can easily integrate your C code, Python code, C++ code, or whatever, and you can use many out-of-the-box component to interact with sensors, with actuators. So if you have questions, this is our approach to support universities in that regard, to make this free of charge for students. I would be open for questions here, but I'm sure the other panelists also have good solutions for universities.
Yeah, for academia, there's always possibilities, because you want to make sure that when they come into the market, they're familiar with the type of tools that are being used in the market. And at the same time, I think, and well, I can only talk from the Siemens perspective, but I assume that the other companies are doing something along the likes, is that we have engineering services and customization services that can assist customers with specific requests, that instead of just delivering a product, we are looking into a project where we make sure that the product as such is fitted into a method, a process of working where it fits what you are looking to do and achieve. So yeah, there's endless possibilities there.
Yeah, we have a very similar approach we take, and we do develop, different workflows, for example, or different algorithms to make life easier for the engineers. Yeah, and as I mentioned, with the universities, we work quite a bit and make sure that the students are up to date when it comes to knowledge about what is required in the industry, like Robert says.
Yeah. And I mean, all three of us are also highly we are benefiting from universities in this regard, as customers proactively ask us whether we know people with good knowledge of our tools, and if there are universities already using the same tools as in the automotive industry, then I think all of us can benefit from this.
Agree.
Yeah, so I think our conversation is going pretty smoothly, but we kind of have a limited time, so maybe Dr. Sitri, you can wrap up with that.
Right. I think I have a last question about from your point of view. Do you have any plan on doing business with digital twin technology solution in Southeast Asian region?
We already
Yeah,
are
sure.
doing it. Sorry.
So, and which kind of business you will go?
We are working with universities as well, and we are working with different commercial organizations from different industry segments, the mobility, oil and gas, as well as the robotics space.
So most of them is like for the predictive maintenance, right? Application, something like that.
Okay, I put up an argument in the beginning of of this panel discussion, during my presentation. We feel that it's not just the operational data, but also we tie in with all the physics data that you capture during the development process of the product, and tie it in to make a pretty robust digital twin. So what apparently happens is the idea is if something had to go wrong in the physical world, since you have the updated digital data all the time, you can do quick simulations on the digital data and then pass on, the decision to the physical world. So that's what we are trying to achieve in some of the cases like oil and gas, where you have the floating platforms, and it's not always easy to take decisions at site. So we try and give some options, and we certainly with the ML algorithms that we have deployed, it's only going to get better, and the decision-making process is going to be a lot smoother and faster. That's what we perceive.
And the Southeast Asian market is strongly growing. I was in Bangkok some months ago on a future mobility fair, and yeah, you see many new startups there. You can see universities and academia research institutes who are increasing their headcount, and more and more students go into the direction. So yeah, as I said, I'm responsible at DSpace for the Southeast Asian market, and I have a lot to do. So I'm very optimistic that there is many companies researching on this topic in the future. And Southeast Asia has a great potential.
From the Siemens perspective, I can only add that currently, if you look at our portfolio, the Asia Pacific market is one of the most important markets that we're focusing on. So yes, absolutely, that's within our focus with all our products and all the power that we can bring as Siemens.
Okay, I think now it's time for a question from the audience. So I think we have a question from Dr. Pasan. The question says, is there a magic mileage number that determines how many miles driven on simulator will certify the robustness of AV, comparing to real mileage driven on real AV, and with what type of simulator, and do we need standard for simulator? So I think that's our plenty of questions. Any? So
that's all.
Yeah, as this is probably related to ECUs, I can answer this. So there is no magic mileage number. This is often a question from customers: how many mileage or kilometers do they need to simulate? It depends basically on the complexity of the algorithm, and it depends also on whether it is level 2 ADAS or is it already AD. And this is also something which has to be discussed with the authorities, because in the end you need to prove that your algorithm is more robust than a human being. And I think it was in Robert's presentation quite informative that the number 4, that you have 4 times 4 accidents by humans is the same acceptance as 1 with a AV. So there is no magic number, but I think the authorities and also the periodic test inspections that we also collaborate with our consulting department can give a guess when seeing the exact requirements and the exact algorithm. And
I
standard,
think
yes, ISO 26262 is, for example, one standard which is quite common.
Yeah, and perhaps to add to that is the number that you always hear is for an ADAS system is 1 million miles without failures before you can be confident that it's well sufficiently robust. But that still depends on where you've driven. I mean, 1 million miles over a highway in some back country is different than 1 million miles in the city. So you also have to look at the distribution and the kind of scenarios that you encounter for a system like that. If you translate that to the digital world, yes, what does 1 million become? Does it need to be 2, 3, 4, 5? Nobody has the answer yet. And it also greatly depends, because that's what I like about this question. What type of simulator, and do we need a standard for a simulator? When I came into this industry, the first question I asked is, what is the difference between the different companies that are offering these simulation solutions, right? Can you grade them? Is 1 million miles driven in the solution of Altair the same as 1 million miles driven in the solution of DSpace and 1 million miles driven in the solution of Siemens? Right now, there is no comparison, and everybody has their own system, their own sensor models. And even though you see that the solutions from the way they are promoted to the market are relatively similar, each has their own accents. So one company is stronger in a certain area than the other is. Is there a magic answer to this? No. And if there would be, and if anybody has it, that person would be becoming incredibly rich, incredibly fast, because he's the one guy in the world that has the answer that everybody else is looking for.
Mhm.
So I think we are running out of time. Maybe I can give every one of you maybe a minute or two for each of you to give final remarks on digital twin technology.
So, in my opinion, it's not a bubble that's going to burst, and so many technologies that come and go in no time. But this looks like it's going to be there for a long time. It's going to stay. So, companies and countries, universities, as they embrace it sooner, the better. And it's better to fuel this technology and then make it not successful in a shorter time. And that would be my view. Thanks.
Yeah, and if I can add to that, and I'll leave the last space to to Jules. The digital twin is a key focus within Siemens. We really believe that the digital twin is an enabler of a disruption force, and coming to market faster is absolutely something that requires a digital twin. I think you're going to see that over the next 10 years, the digital twin is going to become almost a default solution, not only in mobility, but in a lot of other areas of our lives.
I need to unmute myself. Okay. Yeah, I can only agree to what my previous speaker said, and we also rely on research institutes and universities all over the world to increase knowledge, so that we have a chance to see automated vehicles on the street in the near future, hopefully. And there can't be enough engineers to work on such a great innovation.
All right. Thanks a lot, everyone. Thanks for this nice conversation that we have. And I hope in the future we can maybe get in touch for further information, further discussion. And I think if anyone of the audience have any more questions, you can connect with all of our speaker via email, or if you don't have the contact channel, you can contact us first, and then we can point you to the right directions. Thank you, everyone. So I think this concludes our special symposium for today. And what are we going to do next?
Take a group photo.
We're going to take a group photo.
Group photo. So this is the last request from you. So
yes, yes,
so,
yes, yes. Okay.
All right. 1, 2, 3.
One more. Okay. Wait a minute for everyone to join. Okay, are you ready? Okay, we're waiting for other people to open the camera. If we can. Okay, we allow all them to. Okay, 1, 2, 3. Okay, one more. 1, 2, 3. Okay, thank you very much.
So thank you very much for joining us today. All right. See you next year.
Thank you.
Right.
See you next time.
Bye-bye. Thanks for listening in.
Thank you
Have a
so
good
much.
evening,
See you
everyone.
next time.
Bye-bye.
Bye bye.
Bye bye.